Hi, good afternoon, everyone. We understand that people will be gradually joining, so we'll just make a start on the intro slides. So welcome to our first ever Energy Insights webinar. So here we've got 4 exciting speakers lined up, and we're going to be discussing how can we ensure resilience of the energy system to both climate change and extremes. Next slide, please. So first of all, just some housekeeping. So if you have any questions for the speakers, we will have 2 Q&As during the session. So we'll have one after our meteorology focused talks, talking about climate change and extremes. And then we'll have a full panel discussion at the end for all 4 speakers. So please, if you have any questions for the speakers, you can put these in the Q&A box at the bottom rather than the chat. And you can also upvote questions in the Q&A box. So if you see somebody who's asked an interesting question or something that you might have asked, please do give it some thumbs up. And then, yeah, I can pick out the questions which appear most popular. Next slide, please. And yeah, if you want to make the slides bigger, close the chat and enlarge the screen. And then if you're having technical issues, try a different browser or just leave the meeting and then come back in. Next slide, please. So first, just a quick word on the Royal Meteorological Society and our energy sector engagement. So our hope through the Energy Special Interest Group is that we act as a bridge between the energy sector and weather and climate science. And we do this through energy engagement such as this, so events. Last year, we also published the first State of the UK Climate for Energy report, and we're hoping to publish a subsequent report this year, which will outline the events which occurred over the past winter, which impacted the energy sector. And on the special interest group, it's led by Daphne Signiotti and David Brayshaw. And on the RMET side, there is myself and Hannah Mallinson there. And if you want any more information, you can follow this QR code, which should just pop up here. And next slide. Thank you. I'll just leave that just for a second. Okay, next slide, please, Catherine. So the programme for this afternoon. So first up, we're going to have Hannah Bloomfield talking about why climate change matters for the energy sector. Following Hannah will be Emily Wallace from the Met Office talking about extreme weather and why it's important for the energy sector. Following that, we're going to have a short 10-minute Q&A if there's any points that weren't super clear or anything that you might want answering on those 2 talks. We've got 10 minutes to ask Emily and Hannah questions there. And then we'll go into our more industry-focused talks. So first, Ben Sloman from NESO will be talking about how the energy system operator in the UK goes about using this information and the challenges associated with that. And then Will Hodder from EDF R&D will be talking about how decisions are made in the nuclear industry regarding extreme weather and climate change. And then finally, we'll have a full panel discussion for about 25 minutes to half an hour before we finish at 3:30. Next slide, please. So for those of you who aren't already aware, we have the Met Matters sort of newsletter and blog, which you can sign up to. And this is full of events and other activities that you might be interested in joining. So if that interests you. If you're not already a member of the Royal Meteorological Society, we can highly recommend becoming a member. You get access to the in-house journal, weather, and many other benefits. And you also get discounts on conferences, and you can apply for grants to travel. And I think particularly as an ECR, it's definitely worth it joining up to RMET. And then finally on accreditation. So the Royal Meteorological Society have 2 professional accreditation schemes. So you can become a chartered meteorologist or a registered meteorologist. So these things are really crucial for continued professional development and potentially applying for, I guess, progression in any sort of field of work which involves meteorology. So definitely one to be worth looking at. Cool. So I think that's the end of our slides. So I'd like to introduce our first speaker, Dr. Hannah Bloomfield from Newcastle University. Hannah is a Newcastle University Academic Track Fellow in Climate Resilient Energy Systems. She gained her PhD from the University of Reading in 2017 and has since worked on 5 climate service projects with relevance to energy, transport, and finance sectors. Hannah specialises in modelling UK and European electricity demand and renewable generation. She's also worked on developing these tools for Mexico, India, and multiple regions of Africa. A key outcome of her work has been to improve the accessibility of large meteorological data sets to non-specialists. So take it away, Hannah. You've got 10 minutes.
Thanks, Ben, and thanks to Amit for having me. Ben, can you just confirm you can see the slides okay?
Yeah, the slides all look good to me, Hannah.
Perfect. Yeah, so this first talk in the set we've got is thinking about why climate change matters for the energy sector. So I'm going to give you a bit of a high-level introduction to that. So just to check to start with that we're all very much on the same page here. You know, our climate is changing and we can see evidence of that every day. Taking a image here from the Supplement for Policymakers of the IPCC report, we can see the black line here shows our global surface temperatures since 1950, and then going forwards how our planet is projected to warm under different SSP scenarios. So these are different concentrations of atmospheric gases, with the red ones being much higher levels of global warming and the blue ones much lower. So we've got this unprecedented rate of warming, and one of the key questions is how this might impact energy systems particularly. So one key thing which we see most in the media is this idea of disruption to our energy supply from extreme events. So this is the only thing I'm going to say about extreme events. Emily is going to take this on for the second talk. But these come in all shapes and sizes. We've got the top image here of the aftermath of the recent California wildfires. And the bottom image is taken from Storm Arwen, which is a big event that impacted the UK, where over 30,000 people were still without power a good few days after the event. So other things that climate change might be able to do to our energy systems are put a strain on energy supply. So we often think about demand very separately for supply when we're doing our energy system modelling. So this is an example here, projected increases in energy consumption, the difference between 2012 and then this kind of 2080 to 2099 period over America. So anywhere this is red, it means we have this kind of increased demand needed for extra cooling in the summers in very warm regions. And anywhere it's blue is generally places which are driven by us needing demand for heating, and these places are reducing. So you see there's lots of very localized impacts here, and it might be that some places overall through a time period they're seeing an increase, but it might be very different things happening on the energy demand through winter and summer with climate change. Another impact of climate change is thinking about the efficiency of how a thermal power plant may run, and I'm sure we'll kind of come back to this in a later talk. But if we're generally getting a bit warmer, and a lot of regions are also getting a bit drier, this makes it really difficult for traditional thermal generation, so our coal or our gas, to operate in the way that it traditionally does. They operate at lower efficiencies. And often these power plants need a large amount of water for cooling, which may not be available. The final thing we may see is changes to our renewable resource availabilities. So we're making our power systems loads more weather dependent. You can see on the graph here from IRENA that in 2023, our renewable capacity across the world is continuing to grow. Lots more solar, lots more wind, and some moderate increases in hydropower as well. So with this increased weather dependence, it really kind of matters what's happening to the weather. And we're going to think predominantly for the rest of the talk about these kind of changes in temperature and these changes in potential renewable resource availability. So there's lots of really nice plots you can find in the academic literature, and there's a very nice graph like this also in the IPCC report. But the key point I want you to take from this is that all parts of the world are being impacted by climate change, and many, many parts of the energy system are feeling these impacts. but the particular impacts, so for example here, changes you might see around different regions of the world on hydropower are quite different to what you might say to say heating and cooling demand or even wind energy. So it really depends where you are in the world and what's happening with these impacts. So lots of really different impacts are happening. And the magnitude and the confidence we have in these impacts is also very different. So this is an example of some work I did when I was at the University of Reading. So we've got two little graphs, one at the top here for thinking about total aggregate European energy demand in a future period, 2045 to 2065, compared to historical period. So each different bar is a climate model simulation. So each little black bar here is a climate model, and the color shows the mean over those models for a medium and a high-end climate change scenario. So for European demand, we can kind of see that overall European demand in the future climate is going to go down because we need a lot less energy for heat, for cooling. A lot more energy, less energy for heating in winter, so in winter, spring and autumn, and a lot more energy for cooling in the summer. And you can see that all of these little black bars are kind of doing similar things, right? The models, the exact magnitude we might not be confident on, but the direction we very much are. If you look at the bottom plot, we kind of see for wind energy generation, we're a lot less certain about what's going to happen in the future. So climate variability here plays a much bigger role. And it's very sensitive if you look at the kind of percentage change we might see in the future on the particular years you've selected to compute your results. So we see quite varying impacts across different seasons and across different countries. But this is important to bear in mind, I think, that anything that's to do with wind speeds or precipitation, we're quite a bit less certain than we are about, say, changes in temperature. And we can visualize this from a global perspective if we are to look at, say, these are plots that you can make using the IPCC Atlas. So this is a mean temperature change if we look at 34 different climate models. And they're in a 2-degree warming world under a kind of high SSP scenario. So what I want you to take from this is generally everywhere is getting warmer, but there's more warming happen in this kind of very polar region. And the key thing here is there's not really much hatching on these graphs. So this says that the signal is very robust, really, across all of the land that we could be living on or building energy systems. If we have to look at the wind speed equivalent of this plot, we do see some regions where there are consistent signals. So again, we're looking in a 2-degree warming world across quite a lot of climate models. But there are a lot of regions here where we either don't see any change or a robust signal, or there's very conflicting signals across models. So we hear talk quite a lot about the idea in the media of global stilling. So the idea that there's more blue on this plot than there is green. So more regions of this world, we're having reductions, maybe due to poleward shifts of the Hadley cell and movements of the jet stream. But this is very difficult for us to unpack with climate models. And climate variability is a really big factor here for wind speeds. So I put this plot here of the impacts of climate change on hydropower, mainly to say that it's complicated, to be honest. So some renewables, for example, wind power or solar power, they have a very dominant source where if you want to think about the impacts of climate change, you would go look at the wind speeds or the solar radiation respectively. But you can see here, for example, that the amount of hydropower generation you might get in a region is very dependent on a number of factors. So glacier melt, snow melt, if you're in an alpine region, extreme precipitation, stream flow, also increases in variability, the potential for droughts. So a very complicated renewable to think about. I think I'm just going to skip this one in the interest of time, apart from to say, when we think about winds, variability is very important, as I've said, and quite a lot of our trends in wind speed that we've seen over recent periods can be reconstructed by thinking about large-scale atmospheric patterns. rather than panicking too much about our declining wind speeds. So one big thing that we have when we think about climate change and energy systems is there's an awful lot of uncertainty in the modelling chain. And there's a really strong need for people who think about using climate data to work with energy impact modelers and energy and power system modelers to really understand these scenarios well, because it's expensive to run an energy system model, right? We can't just put all of the possible climate data through it. We need to think about sensible choices. So I leave my summary there and happy to take any questions in the Q&A. Thank you very much.
Perfect. Thank you, Hannah. So just a quick reminder that if you have any questions for Hannah, could you please put them in the Q&A box, and we'll get round to those after Emily's talk. So Emily will be speaking next, and she is a fellow in weather and climate extremes at the Met Office, where her role is to empower government, industry, and the public to deal with extreme weather and remain safe and resilient in our changing world. This builds on a career focused on the problem within the energy sector, championing the use of weather and climate modelling to support clean and reliable energy generation and distribution now and in the future. This has included the use of meteorological information from weather, seasonal, and climate timescales to advise on future energy networks, network resilience, renewable energy projects, and nuclear safety and design. So Emily's going to be talking to us about extreme weather. Take it away, Emily.
Hi, thanks very much. I'll just get my slides up properly for myself. There we are. Thanks so much for the introduction. So I'm Emily Wallace. I'm a fellow in weather and climate extremes at the Met Office and also visiting professor at the University of Strathclyde. As Ben described, I'm going to talk about the effect of extreme weather on the energy sector. And this isn't anything new. So weather has always been important to the energy sector. I've been working at the Met Office on behalf of the energy sector for around a decade now. So sort of problems like the efficiency of gas power stations, the extreme risk to nuclear power, damage and danger to the distribution network aren't new. It's always been there. So what I'm going to focus on in this talk is how that's changing. So clearly one aspect of that is the energy transition. So we've got really clear ambition from government for a clean energy system. We've got action plan from government based on the advice of the National Energy System Operator for clean power by 2030. So there's lots of change we're expecting to happen and will be happening. And obviously that's going to have an effect on the extent to which extreme weather is an issue for the energy sector. So just to sort of be specific about what this means, I'm going to focus on the UK in this talk as well. So for the UK, this is one of the main changes that we'll expect to see is much more renewable generation on the system. Obviously, onshore wind, offshore wind and solar capacity are all expected to nearly double by 2030. That means that we'll need transmission lines, new transmission lines to get the power from where it's generated to where it's needed. In time, we'll be looking at increased electrification of demand, heating, cooling and transport. So that the demand for electricity will be going up. And we'll be looking at greater reliance on interconnectors, changing generation and demand patterns. And so the impact of European weather will be much more important than it has been in the past. So what I'm going to do is play through some UK extremes. So yes, as Hannah pointed out, this is where we'll get all the newspaper headlines, and think about whether or not those extremes are likely to get better or worse into the future. So the extremes that I've picked out, I've got a little bit of everything in here. The 40-degree heat wave of July 2022. Of course, I didn't get to the talk about talking about that one. Storm Babette, October 23, which was really notable for the flooding in eastern Scotland, but also other regions were affected by that one as well. Storm Pia from October 23 had a lot of coastal effects, really strong winds, particularly in Northern Ireland. I'm sure everyone remembers Storm Eowyn from January 25, really strong winds over Northern Ireland, very strong winds over Scotland, and also impacts out into the North Sea. And our winter has seen a lot of that this year. This newspaper headline is from October 2024, but I think many of us feel that it could have been most of the winter this year. Anticyclonic gloom, which is periods of low wind speeds, low radiation, often accompanied, although October it wasn't actually, by cold temperatures as well. making gloomy weather for us over the winter. So thinking about how the energy transition is changing how we're affected by those extremes. As I described, the energy transition will mean that we're having to build a lot more new infrastructure in new places. And that means that we'll have to understand these risks in places that maybe weren't relevant before. So from that point of view, we'll need to understand the risk better. In terms of sort of new hazards, there aren't so many new hazards from the new infrastructure. A lot of them are the same as we've been accustomed to before. So, for example, asset damage, health and safety of people operating those assets are still going to be relevant. The area that's probably increasing here is coastal hazards, where we have a lot more offshore generation, lots more offshore assets, and those coastal assets as well, interconnectors, for example, will be increasing our risk here. The area that's really changing for the transition is in terms of the operation. So I've pulled out a few different areas here, just to sort of focus in on a couple of them. Windstorms in the current system and sort of historical system, yes, they cause damage. There is large fluctuation. The really key change that we're expecting to see is in the cap out. So as a windstorm comes through the UK, as it reaches wind turbines, if the winds are too strong, those wind turbines have to stop operating in order to remain safe. That will cause really rapid fluctuations in our generation, which for the system operator can cause challenges that they need to deal with and also cost to the system. The other one that I really want to focus on is the new compound hazards. So these are hazards that, if you a traditional meteorologist, these are really benign situations, really for most situations. The anticyclonic gloom that I mentioned earlier, and everyone's least favourite weather, that sort of breezy, sunny bank holiday where you want to go to the beach. It's never been a hazard before, but in a future system where that will be a day when we've got a lot of solar generation, a lot of wind generation, potentially we could have periods of time where generation was outstripping demand, which would be a challenge. Obviously, storage could be a saving grace there to sort that out. So I've talked about changes for the transition. Now I'm going to move on to think briefly about climate change. So Hannah talked about the global temperature, the sort of global picture in terms of climate change. Obviously, what most of us feel in terms of climate change is those extremes. That's what the media tend to talk about. So I'm just going to go back through my case studies from previously and look at what we're expecting to see in terms of climate change influence on these extremes. So going back to the 40-degree heat of July 2022, we had attribution studies of that heat showing that it was something that was really very unlikely to happen in a pre-industrial climate. Going forward, we're expecting to see more of it, and it is now something that we are expecting to see. So the intensity and the frequency of heat waves will be increasing into the future. That one's very clear. In terms of Storm Babette, what we know about rainfall for the UK is we're expecting warmer, wetter winters and hotter, drier summers. In the summer, when it does rain, we're expecting more intense rainfall. Storm Babette was an example of rain within a cyclonic system. Attribution study from last year run by the Met Office and other collaborators showed that the storms from last winter were around about 20% more rainy than they would have been in a pre-industrial climate. And that's because we're expecting, and we are already seeing increases in extreme rainfall in the UK. So that the rainfall is set to increase, and we're already seeing that. In terms of Storm Pia, those sort of coastal impacts, whilst the number of storms hasn't got a strong signal, there's really large variability year to year in the number of storms we expect to see. The coastal impacts are expected to increase because of sea level rise. So we'll see greater impacts from storm surge and waves hitting the shore. So back to Aowen, as I described, there isn't a strong signal in the number of storms in the UK. There's some climate projections suggest that an increase in the most intense storms, but it's very small compared to the climate variability. So really thinking about the climate variability and very strong winds is the most important. And finally, that anticyclonic loom, I think this is a really key area to focus on in terms of risk to the energy system, because these are hazards that just aren't that well understood because they haven't been important up till now. So it's one to focus on. Okay, so that's the summary. What I'll just finish with is just to say, we've got these two factors. Risks to the energy sector from weather and climate extremes are increasing, and we're seeing new risks emerging. Climate change is a really important factor, and it's really important that it's understood, but it's not the only one. We are going to see entirely new issues from simply climate variability, coupled with seeing that new technology and those new operations on the system. So it's really key that the Met Office and our customers, collaborators, and I know we're already doing this with many organisations, are using forecasts to make better decisions now, using climate information to make evidence-based plans and investments, use that climate information to inform cost-effective build, and we're already starting to think about that future operation and how forecasts can play a role in that. And I think Ben and will pick up on some of these thoughts this afternoon.
Perfect. Thank you, Emily.
Pleasure.
So if I can ask Hannah to turn her camera back on, and then we can get into some of the questions. Just another reminder for anybody who might have joined in the meantime, please put any questions for Hannah and Emily in the Q&A box, and then the same for the talks that we have coming up with Ben and Will. So I'll start with, I guess, Tom's question for Hannah. So do you look at weighted heating and cooling degree days, and how do these change in different climate scenarios? I guess also within that, it would be interesting to cover why we might consider using weighted heating and cooling degree days. And then there's also a question about whether the world map slides would be available. I don't know whether that's referring to the IPCC ones.
Yeah, absolutely. Good question, Tom. So yeah, we definitely do look at heating and cooling degree days. So yeah, I guess for background for people here, the idea of the heating degree days and cooling degree days is we set thresholds for when people might need energy for heating, or energy for cooling. And if those thresholds are exceeded, we count it as a heating degree day. Or if so if it's colder than a certain threshold, it's a heating degree day. If it's warmer than a certain threshold, it's a cooling degree day. So historically, these are just calculated over country boundaries and averaged out, but that is not particularly helpful, because what's really relevant is where the humans live, and where this actual demand is for heating. So if you're somewhere like Norway, all of the humans are aggregated in a relatively small space compared to how large the country is. So I can put do we have a chat in that? We do have a chat. So I can put some links in the chat. There's some really nice online demonstrators where you can actually look at these changes in heating and cooling degree days in the future. So I can put some links in there. And I can also put a link to the IPCC Atlas, which is what I use to make those world maps. So anyone can do that. And there's loads of options of different fields you can look at, and different types of climate models or different regions. So it's a really nice resource. And there's some good explanation of how to use it as well.
Perfect. Thanks, Hannah. We'll go to Alexander's question for Emily next. So how likely is storm damage for wind turbines in the UK? And how often do we get situations where wind speeds are above that cutoff speed? And then also asks, if this doesn't happen everywhere, can we still benefit from these storms coming through, if not necessarily all of the wind turbines are shut off at that time?
Great, thanks for the question, Alexander. In terms of the frequency of damage to turbines, I don't have quantitative figures with me. It is relatively rare for large-scale damage to wind turbines from windstorms, partly due to that cap-out feature that they have, that it would be more significant otherwise. You can Google where there are quite extreme versions of cases of wind turbines being affected by strong winds, which is quite spectacular to see, but hopefully doesn't happen too often. In terms of that final question around, can we benefit from the increase in wind generation from the storms, even with the cap out? absolutely in terms of the total generation. So generally, if you've got a storm coming through, the total generation does increase, which is beneficial in terms of generating low carbon power. The challenge is that generation can fluctuate very rapidly. So through AON, it was fluctuating really very rapidly. You can look on various websites as to the generation through time. And the cap out over the North Sea was several megawatts gigawatts, get my units right, of generation fluctuation, which for the operator who's having to manage that second by second, it is really challenging. So yes, there are benefits to windstorms, but also those challenges as well.
Great, thanks, Emily. I guess going on to a question for Hannah from Alexander. So do you have any thoughts on how we might go about bias correcting wind speeds to capture particularly the extremes, so the tails of the distribution, especially when the resolution of the models and the ground truth are quite different, particularly in the case of climate change models and future projections?
Yeah, it's a really good question. And that's something I didn't touch on very much, but is very, very difficult. Because often when we have these climate model projections, I talked a lot about the differences, right, between the current climate and the future climate. But really, if you want to put things through an impact model, you need to use the physical data. For example, you need to take your wind speeds, you need to put it through a power curve, and then you need to look at the wind power output at the end. And a small bias in that initial wind speed is going to lead to quite a big bias in that wind power output that comes out the end. So bias correction is definitely a good thing to do. I would say the exact methods you use really depend on what you are most interested in at the end of the process. So I think a lot of people who are thinking about energy system resilience. So if you're interested in security of supply, I think it's important that your climate model is capturing low wind speeds very well, so that you've got a good idea of these wind droughts. And if you're interested in what you were just talking about there with Emily about damages, you need to make sure that that top tail is correct, so the climate model is actually able to be windy enough. Obviously that often they're biased a bit low if you've not got a particularly high resolution climate model. So when I do this, I often use percentile based corrections just to make sure that the important bits of the distribution are well captured. But what is very difficult is to decide what your truth is. So we often use 0.5 as our kind of meteorologist's best guess of the truth. And I think a lot of the time that is the best we can do. But I think it's important to understand that in many regions, 0.5 has biases as well, right? So if you have the options to also look at a few weather stations or to look at another reanalysis product, you might not be able to do anything about those biases in ERA 5 for the purpose of your exercise, but at least to acknowledge that they're there, right? And to know how confident we maybe are about the truth, if we call it that.
Thanks, Hannah. That makes sense. So I have a question for Emily, but I think I'm going to save it for the panel discussion at the end to allow time for Ben and Will. So without further ado, I guess I'll introduce Will, our next speaker. So Will is a research engineer. Oh wait, Ben, you're first.
I think it's me. I don't mind if Will wants to go, but
I'll do Ben first. Ben first.
That's fine.
So Ben is a senior modelling specialist at NESO, the National Energy System Operator in the UK. And as a part of the energy security modelling team, his role involves the assessment of electricity security of supply at a range of timescales. This includes developing forecasts of the variability in generation, demand, and interconnector flows, and the impacts of weather on these. Prior to NESO, Ben lived in Norway, where he worked for a chemical engineering company. He holds a DPhil in mathematics from the University of Oxford. So take it away, Ben.
Thanks, Ben. I trust my slides are coming up okay. All right, I can't hear you.
All looks good to me.
Oh, perfect. Thank you. Great. Yes, so thanks for the introduction. And yes, I'll be talking about some ways in which we use information related to climate change and extremes at NESO. So firstly, who are we as an organisation? Well, the National Energy System Operator was established in October 24 with 3 primary duties. So these are net zero, which is enabling the government to deliver on its legally binding emissions targets, efficiency and economy, so promoting efficient, coordinated and economical systems for electricity and gas, and security of supply, ensuring security of supply for current and future consumers, again for both electricity and gas. And we also have secondary duties around facilitating competition, consumer impacts, whole system impacts, so thinking about energy as a whole and links between systems, and to help facilitate innovation. The chart on the right shows a high-level overview of the activities we undertake in order to perform these duties. So I work within the Resilience and Emergency Management Directorate, and lots of my work focuses on security of supply. But we also have teams working on energy insights, strategic planning, energy markets connections, and system operations. Now, we've been established as an organisation in the middle of a changing energy landscape. So previously, most electricity in Great Britain was generated from a small number of large generators, but now much of our electricity comes from renewable sources, and there's a lot more distributed, and we're also interconnected to European markets. In the future, there'll be an increase in the energy from renewable sources, and the energy will be increasingly distributed and interconnected, and as such will be a more complex system, and so will need to be more flexible. And in this period of change, we have an opportunity to shape what the energy system looks like, and a large part of that is thinking about the impact of weather extremes and climate change. So I'm going to give a brief overview about some of the ways in which climate change and weather extremes will impact our modelling in NESO. So ahead of each winter, we publish a winter outlook to market, and one of the key inputs is a probabilistic assessment of the operational surplus for electricity. And by the operational surplus, I just mean the difference between the total possible available generation and the total demand, including the reserve requirement. And you can see there's a plot here on the right. So the x-axis is showing the daily peak of each day, and the y-axis gives this surplus. And we have a central view here and the 90% range as well. And weather variability is a key input to this assessment, feeding into our demand models and our renewable generation models. And we also combine this with a stochastic view of non-renewable generation. And so as part of this weather sampling, we're clearly sampling extreme weather. And so you can imagine that periods of cold combined with low wind would correspond to the low part of this distribution with the lowest surplus. And so changes to the climate could impact what this distribution looks like each year. Similarly, ahead of the summer, we feed into the summer outlook. So here we produce a probabilistic forecast of the low electricity demand each day. And so it's a similar chart here in blue, but it's showing the central forecast of a 90% range for the lowest demand of each day. And this is important because having low levels of demand can impact the operation of a transmission system. And again, weather is a key driver for this assessment, feeding into our demand and renewable generation models. And the changing climate, as Emily has mentioned, could impact this level of summer minimum demand. We can also expand our view from thinking about just the coming winter and the coming summer to think about what the system will look like in the 2030s. So you're probably aware of the government's ambition for Clean Power 2030, in which clean sources will produce at least 95% of Great Britain's generation in a typical weather year. So looking out to 2030, there'll be significant increases in renewable generation and increased susceptibility to low likelihood, high impact events. And stress periods on the system will be increasingly driven by extreme weather events. So if you look at the box on the right, then within NESO, there's a net zero adequacy modelling team who focus on resource adequacy in the 2030s. And they found that if they're looking at if historic weather were to reoccur in the future, then there's a variability of the impact. And their illustrative studies suggest that the impact would be dominated from a small number of historic years. And so digging deeper into these most impactful weather conditions is clearly important. And they also consider the sensitivity to behavior of storage and interconnectors. And a new report will be published later this year on resource adequacy. So watch this space for resource adequacy in the 2030s. We also think about gas security of supply. So there's a plot here showing gas demand throughout winter over the last 10 years, with the last 3 winters being picked out. And you can see there's a strong seasonal shape, with gas demand having this strong relationship with temperature and wind speed. There's a gas security of supply team, and they're considering questions around the likelihood, potential severity, and length of cold snaps. And they'll produce an annual gas supply security assessment starting for the first time this year in October 2025. And this will consider supply profiles from the UK and Norwegian continental shelves, LNG, underground storage, and interconnectors. We can also take another step away from thinking just about electricity and gas security of supply and adequacy and think about resilience. And this has been touched on by both Hannah and Emily. And so as NESO, we have a license obligation to provide an energy resilience assessment report each year. And this also sits under the Resilience and Emergency Management Directorate that I'm part of. And this is thinking about emerging risks and threats up to 10 years and beyond, and relating to a wide range of the whole energy system. So this will assess the likelihood and potential impacts, the impacts of risks and threats, as well as advice on mitigation as well. And some of these risks and threats will come from extreme weather. So just to spell out a bit more clearly what I mean about this, if you go on the National Risk Register, you can look up some weather-related hazards, and you can read about things like severe storms, drought, high temperature and heat waves, wildfire and space weather. And all these could have potential impact on the energy system in terms of risk and threats to electricity generation assets and substations, as well as the transmission network and distribution systems. And there are also dependencies with other infrastructure, such as telecoms, and potential impacts from cascading failures, so several assets being influenced. And this could come from extreme weather as experienced in the present, but also due to climate change, there could be different types of extreme weather events. And there's potential variation across scales. So there could be differences regionally within Great Britain, or sort of thinking about national level impacts, or also events coinciding with Europe at the same time. So to summarize how extreme weather and climate change is important to our role on NESO, as has been stressed, the energy system is undergoing a great deal of change. There's increased weather dependence and increased distribution, and this is going to be even more the case going forwards. And we also have an interconnected energy system in Great Britain. So there can be these knock-on effects from weather both in Western Europe, but also globally as well. And if we look at the top right here, extreme weather could have a range of impacts. So prolonged still and cold weather has an impact on electricity security of supply, and prolonged cold snaps will impact gas security of supply. In the summer, there could be low electricity demand from a combination of high wind and mild temperature, but also the potential direct risks to energy assets themselves from extreme weather. And as we're in this changing climate, this will change the frequency and nature of these extreme events. And so there are drawbacks if we're only using historic weather to feed into our modeling assessments. So these include the potential impact being dominated by a small number of historic years. And also there can be difficulty in assigning probabilities to the likelihood of extreme events reoccurring or being exceeded if we just have a small sample size of historic extremes. And so with this in mind, we've been undertaking an innovation project with the Met Office, which is funded by the Network Innovation Allowance, which is looking into incorporating the impact of climate change in power system modeling. And so by highlighting this improved weather data, which better captures these extreme events and signals from climate change, we're hoping to improve our modeling processes and better assess the potential impacts to the energy system. I think, do I hand back over to you now, Ben?
That's great. Thanks, Ben. Cool. So we'll now move on to our final speaker, Will Hodder. So Will is a research engineer in the Natural Hazards and Environment Research Team at the R&D UK Centre within EDF Energy. So Will has a master's in astrophysics from the University of Manchester and completed his PhD in mountain meteorology at the University of East Anglia in 2022, specifically on the topic of turbulent flux representation in the Lee of Mountains in NWP models. He did part of his studies at the Met Office as a part of a case partnership, and he co-organised and taught scientific Python courses to academics and CFAS personnel. Take it away, Will.
Thank you, Ben, and thank you for inviting me to speak today. I'm just going to share my slides. Can everyone see them?
That looks good to me. I think you're not yet in presenter mode, but we'll get there.
Okay, I am in presenter mode from my end. Has it updated now?
We can see the slides and we can see PowerPoint. Don't know what needs to change. Yeah, maybe go from the beginning.
And now?
Not just yet.
I have no idea. Sorry about this.
No worries. Plenty of time.
What about now?
Perfect. Looks great.
Great. Okay, thank you very much. So I'm a research engineer in the Natural Hazards and Environment team at EDF UK R&D. And today I will be giving a perspective on how we use information related to climate change in the sector from a nuclear and R&D perspective. So first, EDF at a glance. We operate we're an energy generator focusing on nuclear and renewables. We operate all the active UK and French nuclear power stations. And we're currently also constructing Hinkley Point C, and Sizewell C is in the preparation stage. We're a part of EDF Group, which is an international company based in France, and it operates in the UK and many other countries. For example, we have R&D centers in Singapore, the United States, Italy, Germany, and further afield. And the whole portfolio of EDF is not just electricity production, but it's also, going back to what Ben Sloan was saying, for example, we're also looking at the new novel technologies such as energy storage and hydrogen and flexibility services, which will be part of a solution in a changing climate. So why is understanding the impact of climate change and extreme weather crucial for ensuring the safety of nuclear power plants? Well, to ensure nuclear power plants, or NPPs, that they are safe and resilient, we need to ensure that they are safe and resilient to extreme events. This is a multi-pronged approach. Practicing safety is subject to regulation and the sites themselves. Those sites, for example, use safety cases to define how they respond to emergencies and ensure resilience. But we're also considering safety at the planning and construction stage. So it starts right from the beginning all the way until the end, until we deconstructed the last building after cooperation. Safety is relevant to specific equipment and buildings. For example, the ventilation system or the HVAC, which ensures that the ambient temperature indoors is acceptable. Our climate data is important for determining the height of flood barriers and the drainage capacities. And it's also important to understand the variation in cooling water temperatures, but also how keeping the intakes clear and clean. And then lastly, safety is very important for people who will be working both inside and outside. So this is a health and safety issue. A good example here is the extreme winds. If it's too dangerous outside, we need to know when they can happen, how often they can happen, and how long they can endure. So to summarize why, so as climate changes, the nature and frequency of potentially hazardous weather events change too. By understanding the impact of climate change and extreme weather, we can ensure that our NPPs are resilient now and in the future. I'm going to go briefly over the UK regulation. The ONR has published joint regulatory guidance with relevant environmental agencies and have committed to update this in response to up-and-coming science. So for natural hazards, the design basis that we need to achieve and that our licensees at the nuclear power plants require is a 1 in 10,000 year event. So this is with a 84th percentile sort of conservative estimate. This is basically to ensure that our plants are resilient to an event that will probably never happen. We incorporate UKCP 18 largely, but also other climate models into our safety, into most of our safety cases, and this is considered relevant good practice. And the ONR expects us to periodically review our safety cases, the new data and advances in climate science. So what exactly do we look at? And what exactly do we look at? Our licensees are interested in many natural hazards that are affected by climate change. This wheel here represents part of most of what we look at in the team. So there's flooding and hydrological, this is sea surface temperature, pluvial flooding, which also goes to meteorological. There is sea level rise, and then under meteorological, we look at basic parameters such as rainfall, wind strength, air temperature, but also wet bulb temperature and enthalpy. We look at space weather. We look at biological hazards, mostly biofouling. So, for example, fish and seaweed coming to your intakes. And we look at geological hazards such as erosion. And now, at least 4 of these will be impacted by climate change. Fire, you could say, is also climate change, but I think in this wheel it's more about on-site fire rather than wildfires. So how do we do it? Now, well, I already touched on safety engineers at nuclear power plants developing safety cases and how those are used to help operate a plant safely and resiliently. However, in R&D, we support our licensees in nuclear by providing in-house expertise and conducting technical assessments. A large part of that is statistics and modeling. So we perform work on using a plethora of tools and data. We apply a univariate and multivariate extreme value analysis, regional frequency analysis, hydrological modeling, weather generators. We use climate projections, mostly UKCP 18 for UK applications, but also CMIP6 for abroad, and some things that UKCP 18 doesn't cover. We conduct climatologies to understand the present climate and how the climate projections then relate to that for better context. We conduct sensitivity tests to understand how different models and different data sets impact our results, which could then, so we can make more informed, so our licensees can make more informed decisions based on the results we provide them for their safety cases. We apply statistical downscaling to improve data sets where they may not have high enough resolution. We develop tools that are practical tools that can be used by our licensees as well. We also work with our academic partners and the Met Office to address these challenges. We do this through PhDs, literature reviews, and collaborative projects. I will go through a case study and how we consider it and how we then communicate our results to licensees. For example, so extreme air temperature and heat wave assessment for nuclear power plant cooling systems is how each licensee will use them in the EDF depends on who they are and what timeframes to look at. So, for example, nuclear operation, these are the people who currently operate the running nuclear power plants and provide clean electricity for your homes. They require guidance and data analysis to understand the risk over the next few decades. Nuclear new build, they're at an infancy stage, so they need support for the design of the HVAC, so the heat, ventilation, air and conditioning system, to remain resilient for at least a century. And defueling, decommissioning, so it doesn't stop once you turn off the reactor. They need to be able to anticipate long-term climate risk. So standard R&D practices, when we conduct risk assessments for the present and future climate, we select the appropriate observations. So earlier we talked about ERA 5 and bias corrections. That is definitely something we consider, but it is we prefer observations. Direct observations from stations, because we find these can capture the local extreme weather variability better, but we are also exploring bias correction techniques to do for when that isn't an option. We pre-process our observations, and as said before, we need to estimate extremes beyond the observations. So we go for highly extreme events such as a 10,000 year estimate, and we want a sort of high uncertainty quantile just in case. We select the right climate data and pre-process the climate data, and then using that climate data, we then we then track these extremes that we calculated through the next century. So to summarize, we try to quantify the risks for certain climate hazards. These quantifications contribute to safety cases and comprehensively take into account uncertainties in data and method. Safety engineers and site operators use these safety cases to ensure that NPPs, their constituent components and people, are safe and resilient to climate hazards now and in the future. And this involves updating your quantified risk and safety cases periodically, every 5 to 10 years. Thank you.
Thanks. Thank you, Will. So if I could ask the other speakers to turn their cameras on, please, and we'll go to the open panel discussion. It's gone dark on me. That's better. Cool. So if you have any more questions, please remember to put them in the Q&A box, and I'll get to them as we go through. So I think first is a question for Ben from Tom. So obviously not wanting to get bogged down in the discussion about big energy, scaling back on renewables. Is this making NESO rethink their resource adequacy understanding of net zero goals? Or do you think that this won't make a difference for electricity generation in the UK going forwards? I guess it's maybe not NESO's responsibility to do this stuff, but I'd be interested to hear your thoughts, Ben.
Yeah, I mean, I guess you've summarised that, Ben. So the first thing I want to say is I wanted to paint an overall picture of different areas within NESO and different teams that are looking at these things. The specific resource adequacy isn't my specialism. It's clear we're in an energy transition, and so we know things will look differently in the 2030s, but I don't think we want to comment on individual companies. I would also say that there's looking at different ways in which the net zero transition could affect the energy system. There's a document called the Future Energy Scenarios, which looks at different potential pathways for the transition to net zero all the way out to 2050. So that would be a way of looking into different possible occurrences. I hope that answers the question.
I think that makes sense. Thanks, Ben. So I'll go to the question that I had for Emily from her talk. How do you do extreme event attribution? How do you attribute a specific storm and its impacts to climate change? Because that sounds like quite a difficult thing.
So there is work looking at how we can attribute specific storms. My colleague Fraser Lott is working with Oxford University on particularly that question. The study I referred to was looking at the whole of the 23-24 storm season. So we were looking at the rainfall and the sort of accumulated wind speeds over that period. The result I've referred to was a 20% increase in the rainfall intensity, and that was over the period as a whole. It was using a methodology looking at how that quantity has changed from now back into historical climates. And so generally what you're looking at is trying to compare something that you've observed and look how likely something similar would be now and in historical climates. How you define the specifics of the event can be challenging. It's an art and a science in itself, but that's effectively the approach that's taken.
Cool. Thanks, Emily. So I had a question for Hannah about, so why is there more uncertainty in future projections of wind than there is for temperature?
Yeah, that's a good question. I didn't go into that very much. So the physics of kind of global warming and its impacts on surface temperature is relatively straightforward, right? So we've got solar radiation coming in from the sun, it's heating up the surface, and then we have the greenhouse effect that is happening. So the more we emit in terms of pollutants, the more heat is trapped, which leads to us warming. So that bit we understand well. That's quite easy, relatively easy to put into a climate model. The impacts on things like winds and to some extent precipitation, they're kind of secondary effects. So at the point we have heated up the atmosphere, a lot of things then start to happen. So we have things like our Hadley cells and our Ferrel cells and our global circulation. So our temperature differences between the equator and the pole start to change, and this impacts where our jet streams are located, how strong they are, how far they can extend into the continents. And the responses we see in climate models, to this heating are all a bit different. So some of these models we see have jets that shift quite a long way poleward. Some of them have this strengthening, some of them have weakening or splitting of jet streams. And there's no reason to think that some of these are more right or wrong than others. And a lot of people now use these kind of storyline approaches, such as people like Ted Shepherd have developed to be like, there's lots of things that could happen with future wind speeds and climate models. It's just more difficult for us to unpack. So it makes using climate data really difficult, I think, if you want to do like wind power modeling, because you can't just pick one climate model and assume that what that says is probably what's going to happen. It's better practice to use a range of models, or if that's not possible, to speak to your friendly climate scientist, and based on the kind of things that you would like to see from that model, can you make a choice?
Thanks, Hannah. I guess touching on a few of the things you mentioned there, and a question for Ben, what are the main challenges for essentially getting more weather and climate data in use at NESO? Because you mentioned that there's an ongoing project to try and use essentially more climate data. But what are the main bottlenecks with getting that to work?
So I suppose one of the considerations is if teams look at different timescales. So if you're making a model of demand, for example, within the coming year, then that's different to making a model of demand out 5 years or 10 years time. So there might be different weather variables that you want to consider there. I think that's one of the key bottlenecks. We are always keen to do more and look at data and continuously improve.
That makes sense. Hannah?
Yeah, I think just coming in with that, it's not just in industry, right, Ben? Because even in academia, like I would say I'm a climate scientist by training, but I do a lot of work with energy models, and we're still only just at the point where in academia, where we've got loads of free time, that we can get climate data into energy system models, and even then we're not totally happy with how we're doing it. So given this isn't an industry priority, I guess, because it's not actively keeping the lights on, us doing these resource adequacy assessments, I don't think it's a thing to be criticised that it's not being used loads and loads in companies. I think it's interesting that there are still such big barriers, even in academia, to being able to do it well.
Yeah, absolutely. I guess Emily.
Yeah, I was just going to add to that to say we're seeing a real increase in the interest from organisations such as NESO in incorporating climate information. There's making really big strides in being able to do that to better plan. Also seeing that at Department of Net Zero Energy Security, that plans are being made based on really good evidence, and the more we're working together, the more we're improving the ability to integrate these data sets. So I think it's it's an area there's a lot of focus on at the moment, which is really great to see, because it's absolutely necessary to smooth that transition that we all want to see.
Yeah. I guess just touching on that, and a question for Will, given this uncertainty in the climate change projections, so you might use some combination of UKCP 18 and observations to try and quantify your 1 in 10,000 year event at a specific nuclear site. How do you deal with that uncertainty in quantifying these very extreme events, and what are the challenges of using climate data for that?
So the way we deal with them, it depends what it is. So for example, UKCP 18, the publicly available data set, is only the RCP 8.9 scenario. So we just consider this the conservative scenario, assuming that we're not on track for that kind of warming. That then gives, so when we don't have the ability to see many different scenarios or many different outcomes, we can make the choice, or the argument that we're looking at the conservative choice. So the uncertainties are accounted for in that way. Apart from that, we would process our confidence intervals through whatever statistical method we choose for the time, and discuss clearly with our licensees what these confidence intervals represent. Is it the variation, is it natural variation in the climate? Is it the natural variation based on some kind of bootstrapping method? But to go back to the previous question, if I can add to that, there's a French R&D team, EDF R&D team that almost is almost entirely dedicated to bias correcting CMIP6. And when CMIP7 comes around, they'll just go, all right, next one. And they also, so they absolutely, we absolutely do consider what is a new data set, what is the current data set, and how can we improve it. We have so at least over in France, we've got a benchmark data set against which we can measure the SA era 5 and whatever new iteration of reanalysis will come against. Because when you operate a fleet of over 50 reactors in France and the plants we have in the UK, there is value. Absolutely, there's value in having the better data, because like I said earlier, we would usually choose the conservative option, but there is the risk of being overly conservative when you don't have to be. But at the same time, you need to remain safe. So there's a lot of value in having as good a data set as you can get, and putting that extra work and time into doing these bias corrections and uncertainty analyses.
Thanks, Will. I guess touching on a few of the points that Will raised, how does the Met Office approach quantifying uncertainty and working with, I guess, some of the data sets that are produced in-house at the Met Office, in terms of when you have a client who might want to quantify an extreme event at a specific site? Is there a standard method for this? Are there standard practices that are used, or is it quite case dependent?
I'd say it's really case dependent. We're leaning on specific methodologies and often reusing best practice, but it's got to be case dependent, really, for the same sort of reasons we were talking about earlier. The use of weather and climate information is only going to be used by organisations where it makes a material difference to the outcome of that organisation. What we're seeing with the transition is that the importance of weather and climate is going through the roof. And so the materiality of the weather and climate is also increasing. And so the amount of effort it's worth spending on really understanding it is also increasing proportionally, which is great to see. What we don't want to see is the importance increase and the rate of understanding not move with that. So the sorts of methodologies we can use depends on how important it is to really get a precise answer, really get the best answer. So, for example, previous safety case work we've done at the Met Office for nuclear, where we're looking at really big investments, and it's absolutely critical to get as accurate as you can so that you're not getting too much conservatism in there, which of course is very expensive, but you're getting the right amount so that we're not having disasters into the future. There we've got really sophisticated techniques where we're blending observations, large hindcasts and climate simulations to get the very best answer we can. If the question is more around trying to understand whether there is a climate impact, for example, there we would spend much less time really understanding exactly what that uncertainty is. The sort of techniques that we have available would be sort of simple use of ensemble projections, so looking at the range of simulations that we have for a particular region and particular parameter. But yeah, it's absolutely case dependent, depending on how important it is, which is eminently sensible.
Yeah, that makes sense. So a question in the chat for Ben. So can we better use information from the short-term effects of solar eclipses on surface meteorology to better understand the increasing impact of climate change and variability on renewable energy systems? Yeah, not much specialty.
The short answer is yes. I think, yeah, as we're going to a world where there'll be more solar generation, then seeing those changes in generation due to eclipses does allow us to look into case studies about potential impacts of variable climate going forward. So I think that's a really good idea. Thank you for flagging that up.
Yeah, great. So we've got a question from Claudio here. I think this is a good one for kind of maybe all of our panelists, but is there a database of climate projections, wind speeds that a non-expert in climate science can use? For example, power system engineers need to understand the wind potential of a location and require information not only on the present climate, but also on future conditions. I guess, Hannah, do you want to start?
Yeah, I can start, absolutely. So yes, I think the simple answer is yes. There are places online. So the climate services community is massively growing, and there are a lot of demonstrator projects. So a lot of these provide climate data kind of averaged over small regions. So like the NUTS zones, so very small regions over different countries or at national level. If you want particular grid boxes of climate data, that's less easy to get a hold of. I mean, Emily, you'll probably talk about the UKCP portal, I guess. So that's a good option if you're in the UK. If you're not, you really need to get your hands a bit more dirty. But I think the thing I'd emphasize with this is that you shouldn't just want it as a non-expert. I think you shouldn't take sweets from strangers, right? You should know what you're eating. And I think you should kind of, rather than just being like, well, I need to put my climate projections through my model, I think there's an element of being invested in what you're eating and wanting to understand a bit more about the process. So I guess I'll pass to Emily if you want to talk about UKCP.
No, I can't follow that. I'm not going to come up with a quote as good as that. So I was desperately Googling whilst you were talking to get the links that we can pop in the chat. There's a few places you can go for climate information from Met Office in terms of climate projections. One would be the climate data portal. It's not specifically designed for power systems engineers. It's more for that general view of direction of change, but it does give you a grid point view. It's in GIS format, which could be useful. So I'll pop that in the chat. The other one would be the existing climate data portal that Hannah pointed out. It's not quite so user-friendly, but there is some more information in there. And finally, sort of up the more expert end, the CEDAR archive has all of the climate projections. So again, grab yourself a friendly climate scientist who can help you work through that. As well as that, there are consultations going on at the Met Office at the moment for how what data is produced into the future. I'll also try and get the links for that as well, so that you can. I think there's advisory panels you can be looking to join, and places that you can get information in for exactly this kind of specialist requirements that we know are there. So thank you.
Yeah,
and I think Hannah's, just to come back to Hannah, you made a really good point. Personally, as someone who's not a meteorologist but works in energy, actually speaking to people who are the experts and learning from them, rather than just taking a data set and plugging it in, is very valuable.
so we had an interesting question for Will come up in the chat from Lucas. So you mentioned the whole team in France, or half a team, looking at bias correction of CMIP6 data. They're asking, could you elaborate on the focus of these bias corrections, maybe what they're trying to correct and what the focus of that? And they're also asking, is that internal company data or is this published anywhere?
So the first part of that question, it'll be any diagnostic that is of use to our licensees. Basically, we wouldn't really do it for every single diagnostic in the model. And unfortunately, these process data sets are internal. So I think there might be even, it's not even straightforward for me to access it because it is international. We've got obviously these export control laws. But yeah, it is specific. It'll be client or user specific, but processing that is being done to the data sets.
That makes sense. I had a question for Ben on one of the net zero points. So I think on one of your slides, there was a goal about 95% renewable generation during a typical weather year. And this sort of piqued my interest because I was thinking, is there an exception for an atypical weather year, or is this just a way of sort of quantifying the center of a distribution for what typical weather might be and the generation during that?
I think it's just to really stress that the conditions in which a system run are very dependent upon weather, right? So if you have a period where you have prolonged still weather, then obviously it can be more difficult to run with renewable systems than clean power. The precise definition of what a typical weather year is, you'll have to look into the report.
Yeah, that makes sense. And what are the main challenges for NESO in terms of like the next 5 years? Is it really those days that are very cold, or is it more the low wind days, or is it some combination of these two things?
So there are different challenges at different times of the year. So as I flagged, in the winter, then from a security of supply perspective, then it's cold and it's low wind with sort of high demand and low wind. Whereas in the summer, and I think Emily's flagged this as well, if you have a lot of renewable generation that's embedded, so we're responsible. So NESO has partly come out of National Grid ESO, the electricity system operator. So we still have responsibility for that, balancing supply and demand on the electricity transmission system. But lots of renewable generation isn't connected directly to a transmission system. So if you have periods in the summer where the temperature is such that people aren't using a lot of heating or a lot of cooling, so the demand is quite low, but you have lots of embedded renewable generation, then they're systems as well that we need to think carefully about in terms of managing. I think Hannah has something to add.
Yeah, I was just thinking about, Ben, one thing we haven't really talked much about, but you hinted about it, I maybe should have talked about it and didn't, was hydrogen. So we could see that on your slide about the future energy system, that hydrogen was probably going to play quite a big part in aviation and potentially as a fuel. You know, we're not holding anyone to it, but I think it's very interesting. So I'm now based in Newcastle, I'm actually based in a water group, not an energy group. And, you know, when you talk to people in the water sector, there's going to be, you know, just from the water's perspective, there will be big demands on our water. And that's before we even get into things like electrolysis. I just wondered if, like, in NESO, or, you know, if there's a need for us to think across sectors as well when we're doing these decarbonisation plans, the idea that I could run a simulation and be like, we should build all these electrolyzers, but maybe there's not actually the water left, you know, once the water sectors have their bit, and agriculture and everyone else. Like, is that on NESO's radar?
Yes, so definitely thinking about whole system and whole energy system and the interaction between different energy vectors as well, which includes hydrogen as well as gas and electricity. So yes, thanks for flagging it up, Hannah.
I guess just on that. Oh, Emily.
Oh, thank you. I was just going to point to a really great example I've seen of that sort of intersector link up. A group in Scotland focused on critical infrastructure. They've got a forum for cross-sector discussion around those kind of challenges. It's mostly around the resilience adaptation type challenges as opposed to decarbonisation. But what they're looking at is really space-dependent assessments of risk. So understanding the big picture in terms of the weather and climate risk, and then how do those systems interact in the locations in question. It's just a really lovely example. I'll see if I can find a link to them as well to pop in the chat. Yeah.
Right.
But yeah, certainly seeing it happen, and like Hannah said, it's absolutely critical.
I guess on the hydrogen thing as well, what understanding of large scale storage is NESO sort of planning for over the next 20 to 30 years? And I assume that there's some modelling within these future energy scenarios to account for that. But is it specific to any particular technology, or is it quite open, the storage solutions?
So I don't have an answer off the top of my head, other than that there are lots of people doing a lot of work in that space. They're very comprehensive documents. If you Google the future energy scenarios, I might put in a link which go into detail about the methodology of the work. So I'd point you to there to look into that further.
Cool. Thanks, Ben. So I guess, unless there's any more questions that pop up in the chat, I think we'll start to wrap up there. I think Hannah has the best quote of the webinar with "Don't take sweets from strangers, know what you're eating." So that's definitely something that I'll take away from this. But just in general, thanks for attending. So this is the first webinar. So we do have a second webinar planned at the end of March, which will be focused on industry applications of weather and climate data. So including speakers from the Met Office, Atkins, Newcastle University, and somewhere else, which I'll remember. But it will be in the energy newsletter somewhere. So look forward to that. But I'd also like to thank all of our speakers for giving their time today. And yeah, thanks everyone for attending.
Thank you.
Pleasure. Thanks, Ben.
Thank you.
Thank you.
Thanks everyone.